Now in this lesson, we'll look at lines in 3D space. Line space is a straight line, continues indefinitely in both directions. First, we're going to derive the equations of these straight lines in 3D. I suppose this is straight line that we'll want to investigate, and then there is a fixed point P with the coordinates x1, y1, and z1. They're known. And so, suppose now there is, say, another point called Q. Okay, right here, the Q. And because we would assume that Q can move freely along a straight line, so we're going to call Q x, y, z, because we don't know the coordinates of Q. And so suppose that is another vector that is parallel to the straight line. Let's call that U. And U has the components of A, B, C. And so clearly this U is parallel to the vector PQ and also the straight line, of course. So clearly we can then express PQ vector and as a scalar t times u. And in other words, if I express this as follow, x, that will be x minus x1 and y minus y1 and z minus z1. And that will be equivalent to t times u, of course, components of u, a, b, c. And this one right here is what we call the vector form or the vector equation of the straight line. So this already we have derived the vector the equations of a straight line. But we need something more useful. This vector equation is nice, but we need something much more flexible. So what we're going to do is let's compare the x minus x1 is equivalent to t times a. Similarly, y minus y1 is equivalent to t times b, and so on. And so we able to then write x minus x1 be equivalent to ta, or x equals to x1 plus ta. And also if you compare here or equate this and t times b, okay, you would get y equals to y1 times tb. And finally, if you equate z minus z1 with t times c, product of t times c, that will be z equals to z1 plus tc. And this right here is what we call the parametric form or the parametric equations of the straight line in 3D. And the t has a special name. We call t can be any real numbers, and t is called as what we call parameter. Right, it's a parameter. But surely there is a way for us to express the equation of this 3D, the straight line 3D without involving the parameter, the parameter t, only involving x, y, and z. So we can do that. Allow me to rub off. Okay, so looking at this, the parametric equations, just let us focus on x equals to x1 plus ta. What I can do is I can try to express this, express t as a subject, and that will be x minus x1 divided by a. Okay, and similarly, if you look at these second equations, I should be able to express t be equivalent to y minus y1 divided by b. See, basically I'm just expressing the t as the subject for this equation, and of course lastly t equivalent to z minus z1 divided by c by using the last equation right here to get this. And so well, all three of them are equivalent to t. In other words, I can then write this as follow. I can then say x minus x1 over a is equivalent to y minus y1, because both equivalent to t, right? And of course z minus z1, because this is also equivalent to over c, equivalent to t. And this equation, this form, is called what we call a Cartesian equations of the straight line, because this form only involves x, y, z, and you don't see t. So this is, please try some of the questions and look at the next lesson.